Hey, astronomers. F Train here. It's Monday, starting week 3 of quarantine for all you quarantines out there. Um, so today we are going to talk about something that you guys have probably been waiting to hear about for a while now, and that is supernovas. So, and we're going to talk about type 1A supernovas. There's also type 2 supernovas, which we'll be talking about, I think, maybe tomorrow. Um, so supernovas. So first of all, for do now, what happens to if a white dwarf's mass is so large that even the electron degeneracy pressure cannot resist gravity? So we talked about it yesterday, or not yesterday, but a while ago, the fact that we have all the gravity, the weight of a star pulling it toward the center. And when a white dwarf, when you have a white dwarf, the core is basically dead, so it's not producing any new fusion outward. And so what happens is it collapses to the point where the electrons are getting so close together that they're trying to fuse together, and so that degenerate matter is very, very strong. We also talked about the fact that as it contracts, the temperature doesn't change. So it doesn't. It's not like normal matter. When you contract it, when it compresses, it gets hotter. Okay, so it's basically the electrons that are just holding this white dwarf, preventing it from collapsing any further. Okay. So, and then there's something known as the Chandrasekhar limit. The Chandrasekhar limit is 1.4 solar masses, and basically what that means is that if a white dwarf exceeds 1.4 solar masses, then even this electron degeneracy pressure cannot resist the force of gravity that is pulling in, and it will explode in the most cataclysmic way known, a supernova. So what question does this raise? So our aim today is, how can a white dwarf become a supernova? Why will unburned hydrogen falling into a white dwarf ignite? Well, you can think about that for a second. And of course, we know that the white dwarf itself is extremely hot. And so if you have unburned hydrogen, sort of accumulating on the outside of the white dwarf, it's definitely hot enough to ignite fusion. And this is known as a nova explosion. So you have an accumulation anywhere from maybe a few decades to a few thousand years of accumulation. Then you'll have an explosion. This is known as a nova. We talked about that before. So unfused hydrogen transfers through the inner Lagrange point onto the surface of the white dwarf. The white dwarf has already fused all of its hydrogen, so after accumulating, the hydrogen on the surface reaches fusion temperatures. Nova explosion occurs. A nova can be 100,000 times brighter than the sun. Novas can repeat because after this explosion takes place, it can continue to have that hydrogen accumulating for another hundreds or thousands of years, and every time it gets sort of a critical point, it will explode. Okay. And that additional fuel will also come from the white dwarf. Okay. Now, if the not the white dwarf, the red giant that's next to it. Now, if the mass of the white dwarf reaches 1.4 times the mass of the sun, the electron degeneracy pressure can no longer support the gravitational force. But how can a white dwarf gain mass? Well, there's basically two ways that can happen. It can either merge with its partner, which is relatively rare, or it will fuse, hydrogen into helium. So that its partner will give it hydrogen, which it'll fuse into helium, and that will increase the mass of the white dwarf. Okay, it'll fuse that helium into more carbon and oxygen, sort of add on to the mass of the white dwarf. What happens next? Boom. Now, how can a star's core collapse? Well, obviously, if there's more inward force than there is outward force, then the star will collapse. And as it collapses, very high temperatures are reached. Now, we learned that when high temperatures are reached, generally what a star will do will respond by expanding to relieve those high temperatures. So why won't a white dwarf expand in order to do that? Well, we learned about the fact that degenerate matter has one of its major properties is the fact that as the temperature is not related to the the pressure or the contraction. So so what'll happen then is it won't expand to relieve that temperature, and it'll essentially become a huge bomb. All the carbon and oxygen will begin to fuse into heavier elements, and this is known as carbon deflagration. So a type 1a supernova occurs when a white dwarf detonates all its carbon at once, and we're basically talking about like practically instantly. So you can imagine 1.4 solar masses of carbon and oxygen just fusing into energy all at once, which is, you can imagine, is a huge amount of energy. Now, one of the important things that distinguishes a type 1a supernova from a type 2 supernova is that when, obviously to see a supernova, we're probably going to be looking at the spectrum of that object. So if we look at a spectrum of a type 1a supernova, we will see no hydrogen lines. And why would that be the case? Well, of course, if it's all carbon and oxygen, there is no hydrogen, so we wouldn't expect to see any hydrogen lines. Another important thing about a type 1a supernova is that its maximum brightness is 4 billion times more luminous than the sun. So basically, a type 1a supernova can outshine entire galaxies for a short amount of time. Now, how can this be useful to astronomers? Well, one of the things that astronomers are very interested in is something called standard candles. What is a standard candle? It's an astronomical object with a known luminosity. So why would all type 1a supernovae have the same absolute magnitude? Why don't you pause for a second and mull over that question. And how can a type 1a supernova then be used to measure distance? What is the mass of a white dwarf when it explodes as a type 1a supernova? Well, we talked about, excuse me, we talked about this Chandrasekhar limit, which is 1.4 solar masses. Now, since all type 1a supernovae have the same mass, they will all reach the same peak brightness. And that brightness corresponds to an absolute magnitude of minus 19.3 times 10 to the, minus 19.3 plus or minus 0.03. So think about that. If a type 1a supernova was 10 parsecs away, okay, then it would be almost as bright as, the noonday sun. Not quite. I think the sun's like minus 20 something, 27, I think. But it would still easily be seen in the middle of the daytime. Okay, so here's a little calculation you can make here. If the Hubble telescope can see an apparent magnitude of 30, what is the maximum distance it can measure for a type 1a supernova? All right, so obviously you can use the magnitude distance formula for this. All right, and there's the formula. So you can go ahead and plug in for your apparent magnitude 30. For the absolute magnitude, let's just say minus 19. Calculate, you get 6.3 times 10 to the 10th parsec, which is about 200 billion light years. All right, so we talk about the size of our known universe, somewhere in the 20 to 50 or so billion light years. So you can literally see, outside of our known universe, if it was possible, using a type 1a supernova. So we can easily see anything on the other side of the universe. Now, if you miss the initial explosion, you can still use a type 1a supernova to measure the distance. All right, now because most type 1a supernovae are not going to be something that is going to be really, really bright for us to see. It may be something that's happening, like we said, in another galaxy, and so we can use something called a supernova light curve. All right, and so what happens is the apparent magnitude will decay with time, right? It'll start out really bright, and then as time goes by, it will decay. Now, if you look at this pattern here, all type 1a supernovas follow the exact same pattern. They'll peak, like we said, at about 19.3, negative 19.3, okay? And then they will get dimmer as a function of time. And it turns out that they will all do this in the same manner. Okay, you can see that 0, 20 days, 40 days. Okay, so how can we use this data though if you missed the original explosion? In other words, let's say you look up and you see this type, you see this as at a minus whatever 18.5, and then a few days later it's a minus 18. A few days later it's at a minus 17 and a half, right? You can see it's decaying, and you are able to figure that it must be a supernova. But how can you use that data? Well, what you can do is you can fit your observed data onto this standard pattern, and I'm going to show you an example of this. Oops. Okay, so for example, here's a supernova called 1999 AA, all right? And the blue data is actual data of the brightness of that supernova. And this is the standard curve right here. So what we can do is we can move this until it sort of fits the curve there, right? And you'll notice that when you do that, you will see how the apparent magnitude fits onto here. So you know that when it's at its peak, it was at an apparent, an absolute magnitude of negative 19.3. And you can see that that's going to correspond to an apparent magnitude, and you can even do this little bar thing here. When it's at negative 19.3, you can see that that's going to is about a 15. Okay, and so what you can do then is you can just actually let me go back to that again. Yeah, so using that information, then you can go ahead and use the calculator down here. And so, for example, if I put in a pair magnitude of 15 and minus 19.4, minus 19.4, that would give me a distance of 75.9 megaparsecs. Okay. Okay, so all right, and so here's a couple examples of type 1a supernovas. This is the galaxy M101 in the ultraviolet before and after supernova 2011 FE. So you can see this is the supernova right here, and you can see prior to that, that area right there, you see nothing, nothing like that. Here's another one in the galaxy M88. You can see right here that really bright spot in the middle of this galaxy that's, pretty much the brightest thing there. Okay, so so why don't you go ahead and describe to your homie the difference between a type 1a supernova and a nova. Okay, and hope you enjoyed that. Hope you have a great day, and I'll talk to you guys soon.